the second case. So we have first seen the case in which the two eigenvalues of our matrix are both either positive or negative. And now we're going to see if they have the opposite sign. So lambda 1 and lambda 2 are real, they're different, and their product is negative. If the product is negative, it means that they have one is a positive sign, one has a negative sign. Because they're real and different and each one has their own eigenvector, then we can write it again, the solution as c1 xi1 exponential of lambda 1t plus c2 xi2 exponential of lambda 2t. By now we should have this formula well ingrained in our short-term memory at least. We have one of them that is decreasing over time and one of them that is increasing over time. It's up to you to choose which one. I chose lambda 1 to be the one decreasing and lambda 2 the one increasing. And what happens, it means that the one that decreases over time is important when time is negative tending to minus infinity. While the one that increases over time will become more and more bigger and bigger when t tends to plus infinity. The other way around, when t tends to minus infinity, the exponential of plus something times t will tend to 0. So depending in the direction in which you're bringing the time, one or the other term is getting bigger and bigger. So if we have again our two eigenvectors, xi1 and xi2, we know that, well, any multiplication of xi2 is still an eigenvector, so minus xi2 is also an eigenvector. The same is true for minus xi1. And if we pick a random point, that point has been moving towards the center following the negative eigenvector and away from the center following the positive eigenvector. So this point is partially dragged towards the center by the eigenvector associated with the negative eigenvalue and pushed away by the other eigenvector. So we have this curve that we can see. We can also go in negative time and see how it's pushed away. So when we talk about negative time, what you have to imagine is that all the pushes of the different eigenvectors are reversed. If you have this, then we can fill in for all the other directions. When we have one positive eigenvalue and one negative eigenvalue, we talk about saddle nodes. They are asymptotically unstable because after maybe quite some time, unless you are exactly on the eigenvector going towards 0, if you are anywhere else, you're moving away. Unstable means that if you move a little bit, you don't end up at the 0. And this is what happens in the saddle node. While there is a full line of possibilities that brings you to 0, moving a little bit away from it will bring you to infinity in the other direction. Look also how asymptotically unstable might allow you to get first much closer to the center than when you were starting. So for example, here, if you start on the top right corner, you first move towards 0 before moving away. That is allowed in asymptotically unstable situations. Let's look at the MATLAB code. So here we can choose a positive and a negative eigenvalue. I'm not going to change the eigenvectors. We could play with that as well, but it's up to you. The code will be available, so you can play with it. Here I chose a positive eigenvalue 5 and a negative eigenvalue -1. And I retrieve this plot. Now, because I didn't write which one xi1 and which one xi2, I am not able to understand in which directions things are actually moving over time. What I know is that in one direction things are associated with an exponential of minus t, and in the other direction about exponential 5t, the two eigenvalues I just chose. But I don't know if the situation is from the left top and bottom right towards the center and then away, or the other way around. To know that, because we only know the trajectories and we don't know the directions in these cases, we would have to check which eigenvector is associated with the positive eigenvalue. It's not a hard check. That would give us the full information, but it's not an information that is on this specific plot. It is in phase portraits when we put an arrow. So this is an incomplete phase portrait. As before, I could change the signs and I would retrieve exactly the same plot, because flipping the signs of both eigenvalues means that you're flipping the directionality of the arrow of time. So this plot is exactly the same as the previous plot. The only information is that the time has been reversed, but the time is not included if we don't include arrows.